Everyone, welcome back. Ready for another deep dive. Today we're taking a closer look at something you might think you know pretty well. Protons. Yeah. You know, those little guys with the two up quarks and one down quarks. Textbook stuff, right. Well, buckle up, because we're about to go way beyond the textbook. We've got Ethan Siegel's article, Protons, made of quarks, but ruled by gluons from Big Think. Plus, a whole briefing on the topic, and let me tell you, it gets pretty mind-blowing.
Oh, absolutely. It's kind of like you open up the hood of a car expecting to see, I don't know, a simple engine, and then BAM! It's like a whole spaceship in there.
That's a perfect analogy. So
Yeah.
let's start with that basic picture of the proton. You know, the three quarks hanging out.
Right, the classic image.
But then physicists measured this thing called the proton's magnetic moment, basically, how strong of a little magnet it is. And the results, well, they were totally off the charts.
Yeah, if protons were just those three quarks, the magnetic moment should have been way smaller. We're talking almost 3 times larger than they expected.
Whoa, okay, so that unexpected magnetic moment, was that like the first clue that something else was going on inside?
Exactly, like a flashing neon sign saying, hey, there's more to this story.
Okay, so that's where the mystery really starts to unfold.
Exactly. And that mystery led to the discovery that protons are way more dynamic than we thought. Remember those 3 quarks? Well, those are just the valence quarks. Think of them like the permanent residents of the proton. But there's also this whole sea of other particles constantly popping in and out of existence inside the proton.
Wait, hold on. So it's not just those 3 quarks hanging out there? It's more like a bustling city inside each proton?
Exactly. We've got gluons, which are kind of like the glue holding everything together, and then all these other quark-antiquark pairs just popping in and out, adding to the chaos.
Okay, so not just a 3-quark party, more like a crazy rave with all sorts of particles coming and going. And get this, at higher energies, like when scientists smash protons together at crazy speeds, they mostly see gluons.
Yeah, it's wild.
So is it like we need a more powerful microscope to really see what's going on inside these protons?
Exactly. That's at low energies, we're just seeing the tip of the iceberg, but at higher energies, bam, the whole hidden structure is revealed.
Wow, so those gluons are really stealing the show at those high energies. It's almost like we thought the quarks were the stars, but they're more like the opening act. And the gluons are the headliners.
That's a great way to put it. It's like the gluons are the real driving force inside the proton, at least at those high energies.
This is blowing my mind. So if protons are so gluey at these high energies, where do the quarks even fit in?
That's the million-dollar question, isn't it? It seems like they're still important, but their role might be more subtle than we originally thought.
This is incredible, and it makes you wonder what other surprises are hiding in the subatomic world, just waiting to be uncovered.
Absolutely. That's what makes this field so exciting. There's always something new to discover.
All right, so we've got these protons buzzing with activity, and gluons are playing a bigger role than we ever imagined. But what exactly are gluons? Like, what makes them so special?
Well, to get that, we need to talk about the strong nuclear force. It's the force that holds the nucleus of an atom together.
Oh, yeah, the one responsible for nuclear energy and all that.
Oh, exactly. Super powerful stuff.
But I'm guessing it's not as simple as magnets, you know, with opposites attracting and all that.
Nope, the strong force is a whole different ballgame. Instead of acting on electric charge, it acts on something called color charge.
Color charge? Wait, so are we talking quarks that are literally red, blue, and green? Like little rainbow particles?
Haha, not quite. It's just a way physicists describe this unique type of charge. Think of it like primary colors. Yeah, red, green, and blue. Just like you need all 3 to make white light, you need all 3 color charges for a stable particle like a proton.
Okay, I think I'm starting to get it. So these gluons are zipping around, exchanging color charge between the quarks. It's like they're constantly juggling these colors to make sure everything stays balanced inside the proton.
That's a great way to visualize it. But there's a twist. Unlike electromagnetism, where the force weakens with distance, the strong force actually gets stronger as quarks move apart.
Whoa, wait a minute. That's like saying the further you stretch a rubber band, the stronger it pulls back.
Exactly. That's a perfect analogy. And that's what gives protons their unique, gluey nature.
Okay, so I'm guessing that's why we see so many gluons at those high energies. It's like stretching that rubber band so far that all you can see is the rubber band itself.
Precisely. Remember the city analogy? At low energies, it's like we're looking at a blurry satellite image.
Right, just the general layout.
But at high energies, we zoom in and suddenly see all those tiny interactions happening between the buildings, all that bustling activity.
Yeah, it's like switching from Google Earth to Street View. We see the nitty-gritty details.
And the Big Think article uses another great analogy to explain this. The shuffleboard table.
Oh, this should be good. What do shuffleboard tables have to do with protons?
Imagine the three quarks as pucks on the table. At low energy, our probe is like a big pizza stone likely to hit a quark directly. But at high energy, the probe is more like a tiny dime, more likely to slip between the quarks and hit the gluons, in between.
So our view of reality, or at least of the proton, actually changes depending on how closely we're looking.
Exactly. It's like how a city looks completely different from a plane versus walking down the street.
Wow, so at low energies, the proton appears mostly quarky. But at high energies, bam, it's all about the gluons.
That's what the data shows. And it raises a huge question. Are protons basically just giant balls of gluons with a few quarks mixed in?
That's a head-scratcher, for sure. It really makes you question what we thought we knew about the fundamental building blocks of, well, everything. All right, so we've gone deep down the rabbit hole with protons, from simple quarks to this whole crazy world of gluons and color charge. It's pretty amazing how much our understanding can change when we really start digging into something.
You know, it really shows you that there's always more to learn, no matter how basic something seems.
Absolutely. But this whole idea of protons being dominated by gluons at high energies, what does that even mean for like the bigger picture?
Well, that's the really mind-blowing part. I mean, think about it. If something as fundamental as a proton is way more complex than we thought, what does it say about everything else in the universe?
Yeah, I mean, neutrons, atoms, molecules are all built on these fundamental particles.
Exactly, and this discovery about protons kind of shakes the foundation of what we thought we knew about the building blocks of reality.
It's like we thought we had the blueprint figured out, and then someone comes along and says, wait, there's a whole secret underground level you missed.
Haha, that's a great way to put it. And it really makes you wonder, what other secrets are hiding out there? What other particles might be way more complex than we currently understand?
Right. It's both exciting and kind of intimidating, like we're just scratching the surface of what's really out there.
Definitely. But that's the beauty of science, right? Every answer just leads to more questions and more discoveries.
So after all this talk about protons and gluons, what's the one thing you really hope our listeners take away?
That's a good question. I think the biggest takeaway is to never stop being curious. Always keep asking questions and digging deeper, because there's always more to learn.
I love that. Embrace your inner scientist and never lose that sense of wonder. Well, on that note, we're going to wrap up this deep dive into the proton. It's been an incredible journey, and we hope you've enjoyed it as much as we have. Until next time, keep exploring, keep questioning, and keep that curiosity alive.